My name is Amit, and I'm one of the co-founders and the CEO of this company called Luma AI, and I'm going to tell you a little bit about that, but I think mostly I want to talk about what goes on behind the scenes within a frontier model lab, especially one that is not a gigantic company. How do you actually, tame all the chaos? And I named this talk Executing on the Bitter Lesson, because I think that's the founding principle of most of AI, and if you're not familiar with it, I can talk about it for just a second here. So this is sort of what I want to talk about, the bitter lesson. What we do, just for the context of telling you a bit about what I'm going to talk about. Then the meat of it will be the scaling training, scaling inference. And I also have the ultimate solution of how to do this. So if you hang around, you'll see that. All right. So if you're not familiar with the idea of the bitter lesson, it's this essay from Rick Sutton. And, it's basically, people ignore it at its own peril. So let me kind of talk about what it means. So the biggest lesson, there are actually 3 tenets to the bitter lesson, and here I'm talking about 2 of them. But the biggest lesson that we have learned from pretty much all the research and all the work that has gone into AI and machine learning research is that the only thing that works are general methods that are able to leverage all of the computation and all of the data that is available. If you deviate from that, things get interesting. So right now, it might be if you're familiar with this space, this is not going to be a surprise. But if you're not familiar with this space and are wondering why so much activity suddenly, it's because we actually found a general method, and that's transformers. The attention is all you need paper. It's very simple. And it parallelizes insanely well, and it can act on every ounce of data we can provide it, and with some good engineering, every single transistor we can run it on. So that's why you're seeing the activity in this space. That's why you're seeing all the solutions in this space. But yeah, this is the only thing that works. But human instinct is different. We want to learn, right? We want to have an intuition about how something is working, and take that intuition into predicting outcomes, and most importantly, into hand engineering heuristics. This doesn't work. It might give you a very small advantage in the very short term, but in the long term, this has always proven to be a detrimental approach. In fact, it is actually counterintuitive, but any time spent hand engineering heuristics is time wasted not building general methods. Time wasted not actually scaling, the bitter lesson. So that's the bitter lesson. If you're not familiar with it, if you're familiar with it, you can wake up now. But the main bit is, it can't be taught. Bitter lesson cannot be taught. It is so counterintuitive to humans, it just cannot be taught. It can only ever be learned. And it can only be learned with just immense pain. You have to fail a couple of times. You have to actually see the effects of hand engineering things, and then see some other approach pass you. That is the only way people learn bitter lesson. I mean, you're going to hear it, if you're hearing it for the first time today, it's going to sound all very reasonable, all very good. But when you go actually working on the things and implementing them, I guarantee you're going to go towards the non-bitter lesson approach, because you're going to be like, oh, well, if I can engineer this a certain way, it's going to be great. But it just cannot be taught. That's the reality of the world. So let me tell you a little bit about Luma, now that you're familiar with the first part of the talk, which is the bitter lesson. So what are we doing? We're solving intelligence through a different approach. We're scaling data 1000x, and instead of building LLMs, which mean language-limited models, instead of building just with language, we're taking the bitter lesson approach, which is all the data, all the compute. And most of the data is not just in language or text. It's in video, it's in audio, and other modalities that humans interact with literally every single day. This is our research thesis, and to solve this problem, we are training a category of models that are called early fusion foundation models. And early fusion means all these disparate sources of data don't look so different to our models. They are attended to, and they are consumed as one unit. So to our model, just like to a human brain, it's all the same. And this is how we believe we'll build capabilities that are unattainable for language-limited models today. A very small version of that is this model we released called Dream Machine, if you're not familiar with it. It's a video model, and it exposes only one facet of our model's capabilities. We released it about 2 months ago, and it is at about 20 million users at this point, and immense amount of really funny, really cool, really interesting things that people are doing with it. And people are using it mostly because, by some measure, it's actually the most popular video model in the world at the moment. People are using it because it's an intelligent model, not because it's the video model. There are a lot of video models in the world, but it does things with respecting causality, respecting physics, but also respecting intelligence. So that's Dream Machine, and that's okay. To give you a little bit of sense of scale and what we are doing, I won't go through like all the metrics here, but parameter count and data that is used for training. So GPT-4 and Llama 70B, this can also be Llama 405B, which is 405 billion parameters, of course. It's trained on about 15 trillion text tokens. That's about 45 terabytes of data. Of course, in memory, that's much more, but yeah, same order of magnitude here or there. Dream Machine, on the other hand, the first one that's out publicly, it's trained on about 8 petabytes of data. It's a pretty small model, honestly, but it's trained on 400 trillion tokens. Of course, they're not apples to apples, right? Text tokens, but these are still latent tokens. I don't mean pixels. I don't mean the raw information. This is the latent tokens that a model consumes. And the one we're training right now, it goes in the quadrillion range, and I think it sounds really unbelievable, but that is currently what we're doing. So this is the challenge, and this is what we need to scale for. So that's what I'm going to talk about a little bit of how to execute on bit lesson with vast compute, general algorithms, and all the data. I won't be able to go into specific algorithms at the moment, but I do want to give a little bit of a glimpse of how much of a dumpster fire it is to work with technology in this space, and how much energy and effort it takes to actually build these things. So let me talk about scaling training for a bit. So our training currently runs on thousands of GPUs. It's closer to 10,000 than it is closer to 1,000, without going to very specific numbers. Funnily enough, hundreds of nodes. A node is node is 8 GPUs. So about more GPUs fail every week in our clusters than most people have GPUs, and this is pretty standard. We're not underpowering them or anything like that. This is about the failure rate of these very cutting-edge, high-powered machines. We hit storage stack limits every single day, because if you are pumping that much data through a training algorithm, it's gonna have some fun. And I don't mean storage stack on on your hard drive or things like that. I mean S3 storage limits. We hit S3 throughput limits, these kind of things. And finally, cross-node comms, when these nodes have to talk to each other, it's really fun. You would think, okay, if training is running on 5,000 GPUs, if I increase the number to 10,000, it will go twice as fast. No, it actually probably is going to go slower, because all those GPUs talking to each other, there's an immense amount of penalty that you pay on it. So how do you scale compute and training? So you're going to see some choice language here, but taming GPUs and working with them. On the right, you see the graph which shows things coming online, things coming offline, GPUs dying, GPUs keeping alive. If you have ever tried to install CUDA or Nickel, these libraries, we have to run those at a scale of 10,000 or so in inference and training. And yeah, there's some really on the right you see someone writing commit messages or node errors. So working with these machines is that kind of thing. This is early in our life, in our journey. So we have had to build an incredible amount of tooling to make this reliable, to make it so we can execute on really, really ambitious things without everyone just always pulling their hair off. So how we do that? It seems from the outside very simple to you rent some GPUs, you have some open source algorithm, you go run it, right? That's what people think. No, complexities come when the number of some GPUs is a lot. Open source algorithm is not. It's something you're building custom, and you can't just run training. So we have had to go deep into the understanding of the hardware stack that includes the libraries, that includes the GPUs, that includes all the interconnect in between them, in order to build tools that can actually diagnose these problems, right? Not fix. Fix is a whole different ballgame, but to diagnose these problems. The nickel family of issues, the InfiniBand issues, unreliability between nodes. And so see, GPUs are not the only things that fail. Memory on the machine fails, interconnect fails, slows down, those kind of things. So we have done an immense amount of work on this tooling, and believe me or not, over the last just like couple months, to bring it to a place where, like, because we have had doubling of our compute in the last 6 months 3 times now. So like, every time we do that, there's a whole new class or category of issues that show up. So deep familiarity with these tools, with like, the stack in NVIDIA side, on AMD side, all those, right? Like, and none is better than the other. It's all the same, basically. So you need to understand these things at a level where, you can actually deal with them, diagnose them, tell cloud providers what the problems are, all those kind of things. And most importantly, you need to build training stacks that are fault tolerant to that. Because, and we haven't fully succeeded in it yet, by the way, like the last part. Our runs still die, and like, we wake up in the middle of night, or someone is like, on the other side of the world who's like actually manning this to make sure that, like, the training doesn't stop. And the training must not stop. So large labs have published, like, if you especially read the Llama 3 paper, it talks about in great detail the tools they have built, but this is at meta scale. On the other hand, a 40-person team running just about 1/8 or 1/10 the compute that Meta is running is very different. We are not 1/10 the size of Meta. We are 100th or 1,000 the size of Meta. So it's a very different ballgame. But the outcome of that is you can do some incredible things. Second problem is data. So these are cluster names: coconut, banana, peanuts, lime. The Unicode in Sheets doesn't understand that. Melon is another one, and this is the throughput, and I blanked out the unit up top. The unit is actually videos. It's not images. It's not like small things. These are coming in at a billion scale a day, basically. And on the bottom, you see one of our cloud, very helpful cloud providing partners telling us that, hey, we understand your need, but there's no way to solve the network saturation because we didn't build a data center for it. I didn't know you could run out of space on buckets. Right? I don't know if you guys knew that. You can run out of space on buckets. And I don't mean like a second tier, third tier cloud provider. I mean a first tier cloud provider. So when you do new things, these are the problems you want to solve and you need to solve. Now, for some people, this is very scary and this is very arbitrarily difficult and something to run away from. For us, this is actually the most exciting and interesting thing. So, the solution. How do you work with this much data? How do you actually build it? By the way, I didn't include it, I forgot to. So we use very, very simple abstractions, very, very simple things. We just use Slurm. Right? We don't use Kafka or really, really involved solutions. We use the simplest, most boring possible lower level technologies because we are doing already the most exciting things on the top of them. If the ground is also so unstable, that's not going to work out. So use very simple things, very simple abstractions. If someone is telling you, hey, store your data in databases, this level of data, there's no database that can actually take in this level of data. Doesn't matter how much you shard it, doesn't matter what you do. Just use Unix file systems, right? Instead of having queries be in very complex languages and things like that, just store static data. Recompute if you must, right? We run data processing on hundreds of thousands of machines, but recompute it if that's necessary. But keep it very, very simple and understand computers inside out. So in our hiring interviews, we pay a lot of attention to one thing, which is, do people understand computers? And you'll be surprised how few people actually understand computers at a level where, so we break networks all the time, we break storage all the time, we break, these kind of primitives where, it's considered given. But that's not true. Computers are actually very fickle. Even those layers are not solved yet. And you need to understand computers inside out. It takes that level of engineering. And again, it's not complex. There are not many parts to it. It's complicated. They're just, if you don't know what you're working with, if you don't understand ports, these are the kind of things that happen. If this comes as yeah, of course, this is normal thing to you, then I would love to talk to you after this because, we need those kind of people. And yeah, negotiate storage pricing, Jesus. It can get arbitrarily expensive very, very quickly. So you'll be surprised what kind of rates you can get. Another thing here is cross-node communication. So if you're dealing with a vast number of GPUs, so it doesn't matter if 256, 512,000, it doesn't really matter. This comes into play when your clusters go beyond 4,000 and so on. You deal with issues where, like, how you architected your model will affect how fast it can train. And I don't mean like, 1 day of difference in training. I mean between 45 days and 30 days. I mean 6 months or 4 months, that kind of difference. And this is just like, so you get deep into profilers, into networking, into figuring out how are GPUs talking to each other? What is actually going on? What is the size of packets? How often they're being exchanged? Are there any blockers? Are there any synchronization primitives that are stopping things from progressing? It's fascinating. And you learn these very fast, and you need people on the team who can understand these things, can actually execute on them. From this, actually find problems, where the problems are. What is supposed to be there? What is not supposed to be there? These kind of things. So the solution to cross-node comms, and yes, there's no silver bullet, by the way, but the solution is basically, or actually, there's a second category of problems I forgot, sorry. Data loading. If you're familiar with this problem, how do you load that much data on thousands of machines? And I mean a lot of data. A batch size is more than a human's entire life's consumption of video, right? One batch size, and a batch goes on in less than a second of training. You constantly have thundering herds. Each GPU, so here's one thing. All these machines are deeply interconnected, and they operate, the whole thing is successful when all of them operate like a single computer. So they make requests at the same time. They do everything at the same time. So all of these machines will go and hit your storage, hit your network at the same exact time. The problem is called thundering herd. And in computer science, we try to solve that by staggering things. We can't stagger things here. That's not a solution. That's actually, it's gonna now stall the GPU. You can't stall the GPU. The training must go on. So yeah, data loading is a pain. You need to, I'll talk about how we worked on that. Comms efficiencies add up to outrageous amounts, and stock kernels suck pretty much in every framework. Some of you might say, okay, JAX is better, PyTorch is better this way, JAX is better this way, TensorFlow is better that way. That's fine, it's true. In those specific ways, it's better, but in aggregate, they all are very suboptimal for doing large-scale new things. So if you're doing small-scale new things, you're fine. If you're doing large-scale but old things, you're fine. But if you're doing large-scale new things, it's going to be some fun. So how do you solve this? Data load aside, we constantly work on it. We basically race our algorithms and our data loaders. When our algorithms get better, the training side of things, our data loaders become bottleneck. When our data loaders get better, our algorithms bottleneck. We just constantly raise them until we get to a good outcome. Custom kernels, we write a lot of them. We have people on the team who rank in the top 5 in the world on CUDA side of the world, and we write these kernels, wherever we see inefficiencies, we write custom kernels. We design our models with scaling in mind. You can actually design really, really potent, good architectures, right? It's not gonna work. This is the hardware lottery. GPUs are a very specific kind of machine. Networks are a very specific kind of topology. They're built for a very specific kind of thing. And if you design, yes, anyone can think of a neural net architecture. Neural networks are universal function approximators, and you can do whatever, right? But the question is, can you do that in a reasonable amount of time? That's where the problem comes in. So designing models that are with scaling in mind is a very different ballgame. And you test and you test and you test until you're sure that this is gonna run on thousands of machines. And yeah, again, you need to deeply understand the hardware and the underlying stack. There's no alternative to that. There's no abstraction you can come up. You can go to a compute provider that's giving you a nice abstraction. Yeah, you can do some stuff there. But when you actually have to work on something groundbreaking, yeah, you need to understand what you're doing. That was training, and in the interest of time, I'm going to talk about scaling inference very quickly. So We crossed 1 million users in about 4 days when we launched. So here's something funny. I was like, 400 GPUs should be enough for inference. Who's going to pay attention to this? But we crossed about, we were anticipating 1 million users in a year or so. We crossed 4 days, which was a day faster than ChatGPT. It was actually the number of generations were just wild. The amount of usage, we had queues that were in hundreds of thousands, and that was after adding just insane number of GPUs. So as a very small team, we had to, and small team of 4, the inference people are yeah, that's it. We had to scale from these 400 to 4,000 GPUs in the span of about a week. And we had to go that on every cloud provider ever. The best advice in cloud computing is don't go multi-cloud. That doesn't work though when you're at this scale. So basically 9:59 a.m., 6:18, 1 a.m. My chief of staff and I, we basically became day traders of GPUs. At this point, we know who has what capacity, where, at what price, and what configuration. Every single week by week, we know that very well now. But yeah, this forced us to become day traders of GPUs in thousands of volume, and so basically we did that, and we continue to do that actually today. It has not died down. Dream Machine's best days are they continue to be at this moment. But those were early days. We, June, long time ago. Now, we have very good tooling, very good understanding. We run a 5 megawatt cluster. This is actually quite old. We run a 5 megawatt, inference cluster at this point. It's not one cluster, it's everything. But they're all unified in one place. And, for our engineers, it's just one abstraction. They don't have to worry about, targeting all these different cloud providers. Our infra folks do really, really great work. And I say folks it's a big team. It's 3 people. And they do insanely good work so that, engineers and researchers don't have to think about where this model is going, where it's going to be deployed, differences in compute and training perf, all those kind of things. It's all taken care of. But yeah, so that was on inference. I promised you I'll have a solution. I think that was clickbait. So the solution is actually the only one thing. I mean, I would love to find a solution, but the solution is only one thing. If you're going to do something that is new and important in the world, then you need to find the most uncompromising, relentless, and intelligent people. There's just nothing else that works. There's no tool, there's no SaaS service, there's no providers, there's nothing else in the world. Because the problem is, you're not re-solving a problem that has been solved somewhere else, right? You're solving new problems. So how do you do that? You don't need a 400-person team. You need a small team of really, really good people, and they are aligned and motivated to do one thing, the thing that everyone is doing. So the thing we believe is that progress of human society is bottlenecked on intelligence. This is a very core belief that we hold, and it's not a far stretch to even think about, right? Most of the very, very important problems we face in front of us, whether it's in healthcare, how do we increase the lifespan of people? How do we actually, solve materials and climate change? Those kind of things. They're all gated on how many things can be tried. How do we find solutions in the immense volume of data that comes from, healthcare systems, or not healthcare systems, human body. One single body produces the amount of data that is insane. I can talk about this for hours, by the way, but I won't. So the majority of humanity's progress is bottlenecked on intelligence, and somehow we have found a general method in transformers that does scale, that does allow us to pour in all our energy. I don't mean human energy, I mean grid energy. All our energy, all our sand in form of silicon, and all the data we gathered into a machine, and it can give out something really good, right? It's not perfect yet, but it can give out something really, really good. And if this becomes accessible to everyone, that's actually a huge deal. That is when people can try out 1 million ideas to solve problems and those kind of things. In my mind, the solution or the solve with AI is not that you can do something cheaper, you can do something faster. Yes, those are good things. The solve is every person who's interested can try 1,000 ideas, right? You don't have to wait for Marie Curie to stumble upon radioactivity accidentally, right? Accidental discovery is that thing, because the space of ideas is vast, and you accidentally stumble on one. Now imagine if that was not the limitation. So that would be very, very good, right? So intelligence needs to become accessible to everyone, but we just don't believe that language-limited models is the way. People are not going to just constantly talk to their computers in language alone. And most importantly, language limited models, or LLMs, right? Like, they only ever see final human output language form. They never see the world. They never see, like, how the thing came to be. They don't see, like, what human brain sees. So if you have to actually, even if you think about if the goal is to reach human level intelligence, you need human level inputs. You don't have that today. So that's what we're building. And if it is interesting to you and you want to work on really hard problems and work with a group of people that are super dedicated, please come join us. So that's it. Thank you very much.